let's go and review before we get into our final conic. Let's review a couple things about our past conics. First of all, the very first conic we talked about was the circle, right? How did we define the circle, Jamie?
A locus of points a given distance from a given point.
Good. The locus of all points that are a given distance from a given point. So two things really defined the circle, class.
Center and radius.
The center and the radius. And we said if we have x squared plus y squared plus ax plus by plus c equals 0, where we have ones here, or if they aren't ones, we could divide everything by whatever number it is and get ones, right? So if there were 2's right here, you divide everything by 2. 5's right here, divide everything by 5. You're going to get ones in those spots for the circle. That right there defines circle. Then we went to the parabola. And the parabola was defined as, when?
The locus of points equidistant from a given line and given point.
Good. Locus of points equidistant from a given line and given point. The given line was called the directrix, and the given point was the focus. Right? The vertex was part of the locus, but the focus and the directrix defined the conic. And here the big difference was x squared or y squared, right? But not both. But again, we would still get a 1 in front of the x squared and the y squared by the time it was all said and done. And then from there we went to the ellipse. That was a fun one. Jamie, hear the definition, a little more awkward.
The locus of points and the sum of the distance between the 2 points given is equidistant all around.
Locus of points whose the sum of 2 constant distances equals
All right, it's the locus of points, and the sum of whose distances from 2 fixed points is constant. So there's a constant sum of distances from 2 fixed points. Those 2 fixed points were the foci, right? And then the sum of the distances would remain constant. Here, we again have the x squared plus y squared, but we would have different numbers. So you couldn't get a 1 in front of both. And so we accordingly just changed these letters to go alphabetically there. Let's then talk about the hyperbola. So next thing you know is the hyperbola. Now, of all the conics, this is the most unique. Okay, the hyperbola, the most unique. Its definition, very similar to that of the ellipse. It's the locus of points having a constant difference of distances. The locus of points having a constant difference of distances from 2 fixed points. The locus of points having a constant difference of distances from 2 points. So the circle has 1 point and a radius. The parabola has a point called the focus and a line called the directrix, equidistant all the way. The ellipse has 2 fixed points called foci, and the sum of the distances remains constant. The hyperbola has 2 fixed points. Again, they're going to be called the foci, but the difference of the distances is going to be constant. Another interesting thing about the hyperbola is it'll be in the form ax squared minus by squared plus cx plus dy plus e equals 0. It's the only time the squares have a negative. Now you could say, well, what about the a? Couldn't the ax squared be negative? Yeah, but then you could change all the signs, make it positive. Now the by squared is the negative, right? So it's easier to memorize in this form, but the key defining characteristic is both squared, like the circle, like the ellipse. Like the ellipse, the numbers can be different, but a can equal b, at least the integer value can. Now, again, 1's going to be negative, and that's the key. But you could have equal numbers. You could have 2's in both spots, 5's in both spots, which you can't have for the ellipse. That would make it a circle. The difference is you have to have literally a difference, a minus sign. And that might help you remember the definition. The fact that there's a difference, the fact that there's a negative. A couple other key things to jot down about the hyperbola. It has 2 discontinuous branches. The hyperbola has 2 discontinuous branches. This makes it really weird, right? The circle is just nice and perfect. It's a circle, right? The ellipse is like the circle got squished a little bit. The parabola is like it got squished and part of it got chopped off so it doesn't wrap back around. And then the hyperbola, it almost looks kind of like, almost like as if, and it's very poorly drawn, almost like as if it's two parabolas. Now, it's not two parabolas, but it almost looks like two parabolas faced away from each other. And you may remember this actually from when we first saw it, right? When we were doing the intercept symmetry domain and range way back in the day, we saw this a couple of times as well. So two discontinuous branches. Also, what's interesting is there are two asymptotes. There are two asymptotes as well. And that's not true of the other conics. There weren't asymptotes with the other conics, but there are with the hyperbola. So a couple of weird things about it. I want to point out some things here. Like a parabola has a vertex, well, so the hyperbola has two vertices. So the hyperbola has two vertices. And of course, we would draw a line through them. Let's see if we can actually draw a line through them. There we go. We could draw a line through these vertices. And of course, this is one axis to which they are symmetric. Now, you'll recall that the hyperbola, because both are squared, is symmetric to both axes, right? So there's also an extent to which it's symmetric here to this axis also. If we were to look at just the length between the vertices, this here is called the transverse axis. The transverse axis. Now, the whole line is not necessarily the transverse axis. It's the axis of which part of it is transverse, but the transverse axis itself is specifically the distance between the vertices, much like the major axis was on an ellipse. The difference was, on the ellipse, because the vertices were the ends and it ran in between, it was within the conic. Here, it's between the parts of the conic. That make sense? The very center, the midpoint rather, of the transverse axis is called the origin of the hyperbola. The origin. It's not within the conic, so we can't really call it the center of the conic. It's just called the origin. And the origin, of course, will be translated at times. Now, coming right through here is another axis to which things are symmetric, but it's kind of a predefined length. This perpendicular bisector of the transverse axis is called the conjugate axis. The conjugate axis. Now, if I were to kind of take this line here, and these lines here, okay, you could kind of begin to make a rectangle going around. Perhaps the easiest way to think of this would be to take this length and draw it right here tangent to the curve, right here tangent to the curve, and then come across the top. And we'll get a little box that is not in or even part of the hyperbola, but it falls right in between the two branches. This is called the fundamental rectangle of the hyperbola. Fundamental rectangle. I'll use a little geometry abbreviation here. The fundamental rectangle of the hyperbola. It's formed using the lengths of the transverse axis and conjugate axis. So you see, I took that conjugate axis length, put them at the ends, took the transverse axis length, put them at the ends of the conjugate axis, and just form a triangle going around. This is not part of your hyperbola, but it's an important thing that'll help you graph the hyperbola, because really the only part of this you care about are these corners right here. I really don't care about anything else in hyperbola. I don't care about this. I don't even care about drawing this line per se, or this line. I care about only the corners. And we're going to use the corners, and you're going to want a straight edge as you go through this section. We're going to use the corners, or the vertices, if you will, of the fundamental rectangle to draw our two asymptotes. I told you this is the one conic that has asymptotes, and this is where you could tell my drawing of the hyperbola is very poor. So what we're going to do then is from the vertices, we're going to approach but not touch our asymptotes. And the result is then that the hyperbola, more so than the parabola, gets flattened out a little bit. And those asymptotes are going to allow us to get a very good hyperbolic shape. So one of the first things we'll do as we go to graph our hyperbolas, and we're going to practice this in a minute obviously, is figure out where the transverse conjugate axes are, but really it's all about the corners of the rectangle. Draw those asymptotes, that's going to help us to get a really good shape to our conic. Now, I told you the hyperbola is defined as the locus of points having a constant difference of distances from two fixed points. Those points are the foci. One focal point is out here, another focal point here. Just like, there we go, just like the foci are inside the parabola, they're inside the curves of the hyperbola. Does that make sense? But here's the key. The focal length is not right here, like you'd expect. The focal length is measured from the origin out, kind of like it was in the ellipse. But the difference is, remember in the ellipse, vertices are at the ends, foci are inside. Now we've got our foci outside the vertices, and that's why the curve, instead of going in, flips out. Does that make sense? So we're pushing the foci beyond the vertices. And remember, we talked about how if the foci come closer and closer to the center, you get more like a circle. Push them closer and closer to the ends, you get more like a straight line. Well, the question becomes, well, what if we push the foci outside the vertices? Well, now you change from an ellipse to a hyperbola. Make sense? We still have focal chords, though, perpendicular to this main axis we draw that has in it the transverse axis. And of course, we call these the latera recta. So no new names there. And the latera recta work with the asymptotes to get us a really good shape to our hyperbolas. All right, so then, how do we figure out mathematically all this stuff? Some things to jot down. First of all, the transverse axis is from V to V prime. O is, of course, going to be the midpoint of that, and it's always equal to 2A. You're like, oh, this seems kind of familiar. The conjugate axis doesn't have any special points per se, but it's equal to 2B. Just like the minor axis was 2B in an ellipse, and it didn't necessarily have any special points, it was just the perpendicular bisector of the major axis. Here, the conjugate axis is just the perpendicular bisector through O of the transverse axis. It happens to have a length of 2B. So we don't have to memorize new formula here. That's nice. The focal length. And again, this is key. It goes from O to F. Not V to F, O to F. And of course, O to F prime is going to be represented by the letter C. Okay, that makes sense. Here's the big difference. C equals the square root of A squared plus B squared. We're literally using Pythagorean theorem here. And the book goes through showing how this is determined, but basically the focal length functions as equal to the hypotenuse rather than to a leg of a right triangle, where it functions as a leg in the ellipse. The half latera recta, since that's all we ever seem to use, are going to be B squared over A, because the whole lattice rectum equals 2B squared over A. No big deal. That's the same formula we had before for the ellipse, and that's pretty easy. Now here's the big difference. That's A. That's C. You realize C is bigger than A, correct? So when we go to find the eccentricity, it's still going to be the ratio C over A, focal length to half transverse axis, same as it was focal length to half major axis for the ellipse. But because C is greater than A, the eccentricity will always be bigger than 1. It'll go from 1 to infinity. And I say infinity, admittedly, an eccentricity of even 5 is pretty high. So we're not going to get anywhere near infinity on our eccentricities. 5 is really flat, okay? By the way, remember we said eccentricity refers to how different it is from a circle, is a good way to think of it. Well, if it's really, really flat like this, that's nothing like a circle. That's going to have a higher eccentricity. If it's got a really tight curve to it, it just happens to have 2 branches, we still have a lot of curve. Now it's flipped out, not flipped in, but it's still got a lot of curve like a circle. That eccentricity is going to be closer to 1. Does that make sense? So bottom line, you want the focal length to be barely bigger, right? If that focal point is way back here, man, that's way bigger. It's going to be a really flat hyperbola. When the focal length comes in tight, that's a good indication. Okay? Questions on that? All right. So let's get this in the notes. Then hyperbolic form. Hyperbolic form. We had a circle form, right? We had the conic form for all of it, obviously. But we had a circle form, a parabola form, an elliptical form. It's got a hyperbolic form. And the good news is it looks really similar to what you've seen before. X squared over a squared minus y squared over b squared equals 1. Or negative x squared over b squared plus y squared over a squared equals 1. And the key, a squared, is whichever is positive. Now, whichever is bigger, but whichever is positive, which would make it bigger, I suppose, in that sense. All right, so you're looking for the positive one to be the a squared. Questions on all of this? Again, I'm just kind of giving you a lot of notes. We're like, we haven't seen how it works yet. Let's take a look at how it works. Don't get out some graph paper and set up a Cartesian plane thereupon. Zoom in just a little bit tighter here. All right. And write this equation down, if you would. Negative x squared plus 4y squared equals 4. Negative x squared plus 4y squared equals 4. The analysis of the hyperbola is going to be very similar to the analysis of an ellipse, primarily because it's very similar form. The parabola was very unique. The circle was very straightforward. The ellipse and hyperbola have a lot more in common other than their actual shape. Another reason why I like to teach them one right after the other. Just like for an ellipse, the first thing we always found was where's the center? For a hyperbola, the first thing we're always going to find is the origin. And for now, it's going to be at the actual origin, 0, 0. You know it's going to get translated, but for now, we're going to start it at 0, 0. Just like an ellipse, the first question was always, which axis is the major axis? Well, for us, which axis is the transverse axis? And again, the transverse axis is going to be the one that has the positive. Well, which one has the positive, class? Y. The y. So the y-axis is where my transverse axis will be. Make sense? All right, these things we essentially have already answered. Let's get it into the hyperbolic form. And I just erased the hyperbolic form. The hyperbolic form, like the elliptical form, was it's set equal to 1. So to set this equal to 1, we divide everything by 4. And we get negative x squared over the 4 plus y squared over 1 equals 1. Notice, although the number is bigger under the x, it doesn't matter. The y has the positive, the y is transverse. For an ellipse, they're both positive, so you have to make a determination based on size. Here we make a determination based on positive or negative. The next thing we'll want is how big is the transverse axis. And remember we said the transverse axis is 2a, where the positive is the a squared. So the 1 is the a squared, therefore a equals 1. So we could say 1 each, or we could say 2. That's how long the entire transverse axis is, only 2. 1 each. Then, the conjugate axis. Well, again, the conjugate axis is the one that has the negative. But again, this is the b squared, therefore b is 2. So we could say 2 each, or 4 for the whole length of the conjugate axis. Now remember, a major axis has to be bigger than a minor axis. Hence the names major and minor. Transverse and conjugate, the one doesn't have to be bigger than the other. Okay? You could have a square, you could have them the same size, you could have them different. It doesn't really matter which one's bigger, which one's smaller. The next thing we'll find is the focal length. And this is one of the biggest things to keep straight in your mind, is that the focal length is not the squares subtracted, so not square root of 3, but the squares added, so the square root of 5. Or we could say approximately, I think it's 2.2. I think we've used this one a number of times with fact check. Jamie has fact checked and confirmed. And then the half latera recta. Again, it's going to be b squared over a for each half. But remember, the b squared isn't necessarily the smaller number, it's the one that has the negative in front of it. So the b squared is the 4, and the a is a 1, so the half latera recta are 4. Make sense? So let's see how this looks when we graph it. We're going to mark our origin, of course, at 0, 0. And we know the transverse axis is this y-axis. On the transverse axis, we're going to go up 1, down 1. 1 in each direction. There's the origin, there's a vertex, there's a vertex. The conjugate axis, I will not mark with dots. I'll mark with little lines. I'm going to go outward 2 and outward 2. So let me zoom in just a little bit more still. Try to make it that much easier to read. Now, once I've got these marks and I've got these dots, do you see where the rectangle is? It's all of this space in here, right? You don't have to shade it in. What I want you to do is just mark the corners of where your fundamental rectangle will be. That's really the purpose right here, is to get the fundamental rectangle. And the purpose of the fundamental rectangle is because it gives us our asymptotes. So take out a straight edge and connect it to dots to get 9 asymptotes. Here's the key, focal length. This is where students screw it up. The focal length starts at, and it's not on the screen anymore, but it starts at O. We're going to begin at O and go up 2.2 to a focal point and down 2.2 to the other focal point. Not starting at the vertex. Don't go up 2.2 from the vertex and down 2.2 from the vertex. Go up and down 2.2 from the origin, the dead center of the fundamental rectangle. Make sense? Mm-hmm. All right, and then from there we're going to go outward 4 in each direction. And notice this puts us really close to the asymptote. It is not uncommon for your latera recta ends to be near, very close to the asymptote. Now here's the fun part, is the curve. And there's not a lot of curve. The curvature really only happens at the vertex. There's a tiny bit of curve. So what we're going to do is we're going to slowly curve. And it almost looks like we straight lines. You see just a tiny bit of curve there? It almost looks like it's straight lines. And it almost does. And then we'll retrace. And make sure you're approaching but not touching the asymptote. Make sure you're approaching but not touching the asymptote. So again, right here at the vertex, you see just that little bit of curvature. So it's not a V, okay, it's not straight lines, it's got a little bit of a curve at the top, but not much. Ooh, might be cutting a little close to that asymptote there, and then approach but don't touch. And again, like we've done with asymptotes in the past, if you start to get too close, we're like, that's coming in real tight there. Erase it a little bit. Drawing less, not more, is kind of going to be the key. Remember with an asymptote, at no point should we touch it. Okay, here it touches. Okay, that's a problem. At no point should we curve away. At no point should we, it still curves away, should we run parallel to it? It's got to constantly be approaching but not touching. So again, once you get through the ends of L and R, don't go too much further. A little further and we're good. Stop before you run into it. Stop before you touch it. Stop before you curve away from it or run parallel. And that's where the asymptotes get a little bit picky. That's really the hard part about the graph, is making sure you handle the asymptotes properly. But we've worked with them before, so I think we should be okay. Questions on this? All right, let's do another one of these then. By the way, the eccentricity, C over A, is 2.2 for this particular hyperbola. And if I'm smart, I don't erase all of the labels. I will say, because of all the nuances involved in graphing the hyperbola, I'll typically do a new Cartesian plane for each one, just because there's so much stuff involved, which is unfortunate. The lazy mathematician in me cringes. But with the rectangles and the asymptotes and all of that nonsense going on, it's just really hard to try to do more than one hyperbola to a Cartesian plane. So don't make the Cartesian planes too big. Number one, it saves space on the page. Number two, it saves time in setting it up. Of course, I'm kind of limited in how big I can set mine up anyway. But as you're working on graph paper, don't get carried away. All right, and for this one, I might have wished I actually made it slightly bigger now. Oh well, 16x squared minus 9y squared equals 144. First things first, let's set the equation equal to, and what does it become when I set it equal to 1?
X squared over 9 minus y squared over 16 equals 1.
All right. Where's the origin? For now, that's going to be the case. Which axis is the transverse axis? Why?
Because it's positive.
Good, not correcting you, but asking why is it the x-axis? Because it's got the positive in front of it. It's maybe the smaller number, and it could be the bigger number. They could be the same number. It's whichever one happens to be positive. How long is each side of the transverse axis? 3 each. It's going to be a total length of 6. If you wanted to put that as well, but the 3 each is usually what we'll put. How about the conjugate axis? 4 each. For a total of 8. Now remember, the focal length, you're going to take those two squares, add them, and take the square root. 5. Square root of 25, which is just 5. And then for the half ladder erecta, you got to make sure you key in on the b squared and divide it by a, which in this case is 3. And 16 thirds?
5 and a third.
5 and a third, or 5.3. Either way of thinking of it will get you about the same point. Now again, longer ladder erecta, usually flatter. Shorter ladder erecta, usually a little bit more curved. So this is going to be another pretty flat one. The last one was pretty flat, this one's pretty flat. By the way, you could already determine the eccentricity. Focal length over half lattice rectum, we get 5 to 3, which is about 1.7. So not as flat as the last one, but still pretty flat. All right, so start at your origin, 0, 0. And along the x-axis this time, go 3 in each direction. And again, these are going to be your vertices. Then along the y-axis, go up and down 4. I just make that little straight mark. I'm kind of picturing where the rectangle is. So we're going to go from there outward to the 3 and mark the corners of the fundamental rectangle. I'm not going to draw the whole rectangle. Again, I shaded it in last time just to help you see it, but I usually do not shade in the rectangle. Why? Lazy. All right, and then we'll use the fundamental rectangle to draw our asymptotes. And so a good straight edge certainly helps there. A good math teacher would have told you in the last lesson, make sure you have a good straight edge. But I didn't tell you. What does that tell you? All right, my bad. Add it to the YouTube comments on the last video, so at least the video description tells them the finished edge. All right, so get your asymptotes there, going through the corners and of course through the origin as well. All right, now, where do I measure the focal length from? The origin, along which axis? The x-axis. We're going to go 5 along the x-axis, starting from the origin. So out 5 in each direction, and these are the two foci. On my curve, every point on the curve that I'm about to draw of the hyperbola, every point is going to have the same difference of the distances from its own focus and the other focus. Obviously, the distance to the other side's focus is going to be greater, and then so we're going to take that distance minus the distance to its own focus, and that number is going to be constant. All right, through the foci, we have our focal chords, the ladder erecta. They're going to be perpendicular to the x-axis, so we're going to go up and down 5.3, not from the vertex, but from the focus. Up 5 1/3. And down 5 1/3. Up 5 1/3. Down 5 1/3. Again, start at the vertex. And curve so you're approaching but not touching. And retrace. And approach but don't touch. And that may be one of my better branches I've drawn in my time. That one turned out pretty good. We'll look at some computer-generated versions. Of course, you saw some as well in your homework reading over the weekend. Again, you can see a little bit more curvature to this one. Now, it's bigger as well, but you can see a little bit more curvature to this one than you did in the last one. But it's still pretty flat, especially compared to a parabola. Parabola has more of a bowl shape. This, not so much. What with the X on the chest, I almost picture like, you know, one of those like really fit soldiers at Buckingham Palace or something, you know, and it, you know, really trim the waist, you know, a little bit of, but not a lot, not super, that'd be weird, right, on most, but that little bit of a waistline, of course you got the cross over, the X over the chest, just because it looks cool. So anyway, that's kind of what I'm picturing there. A little bit of a nutcracker soldier type, for those in our art class. All right, all right, questions on this? All right, let's do one that is got a little bit more of a curve to it now. Set up the new Cartesian plane while I get my end set up. Negative 9x squared plus 4y squared equals 36. If you want to get a jump on the analysis, you can. See what we call analytic geometry. We're analyzing everything. All right, first things first.
Set equal to 1.
Set it equal to 1. What do I get?
Negative x squared over 4 plus y squared at 9 equals 1.
Origin?
3, 0.
Which axis is transverse? Why? Because it's positive. Not because it's bigger. It happens to be bigger this time. But it's not because it's bigger, it's just because it's positive. How big is the transverse axis?
3.
3 each. We could say 6. How about the conjugate axis?
2 each.
2 each. We could say 4. How about the focal length? The square root of 13. But that's 3.6. All right, and then the half lateral recta. Remember, the b squared is the one with the negative, divided by the square root of this one, the a.
1.3.
1.3. 4/3, which is approximately 1.3. By the way, notice really short lateral recta here, right? That's nice. That means we have more of a curve, more like a parabola, less like a flat line. Also, notice the focal length is only a little bit bigger. If you divided this, and you probably do it in your head, 3.6 divided by 3? 1.2. That's on the really low end for a hyperbola, which means it's going to be a lot more curved than some of the others. All right, so we go 0, 0. And then along the y-axis, go up and down. 3. And along the x-axis, go outward 2. And then get the corners of the fundamental rectangle. Once you have the corners, use those corners to get your asymptotes. All right. Well, once we have asymptotes,
Go down and up from the origin 3.6.
good. From the origin along the y-axis, up and down 3.6. Now again, this means that your foci are just barely outside the vertices, but that's okay because it's going to give you more of a curve. And then through those foci, outward, perpendicular to where the transverse axis runs or the y-axis runs, we're going to go outward 1.3. This is going to have a lot more of a curve to it, doesn't it? Much more pronounced curvature. Oop, that kind of ran parallel. Always lightly in pencil first so you can erase any errors that you may have. And there we go. Questions on the hyperbola? Feel like we've got it? I know you came into the class like, oh dang, it's the hyperbola day to day. Do you feel a little bit more at ease about it now? Not nearly as complex as we thought. I get a lot of similarities in the analysis to the analysis of an ellipse. So coming right off the heels of the ellipse, that's good. Now the hard part's going to be we put it all together, keeping the two straight. Okay, but we'll work on that after we've spent a few days here on the hyperbola. Just two hyperbolas to graph. Again, I want each one on a separate Cartesian plane, and that's page 251, number 1b and 1h. Page 251, number 1b and 1h. We'll take a look at both of these in our next lesson. Have a wonderful rest of your day, and you are dismissed.